So this is a video that describes different trends in the periodic table, and everything has to do with how well the nucleus attracts the electrons. If we understand that, you can explain every trend that we're about to talk about. And so where we're going to start is this idea of effective nuclear charge, and then we'll talk a little bit about atomic radius. And so, effective nuclear charge, what is it? Well, obviously, the nucleus has a positive charge in it, but the question is, how much of that charge does the outermost electron really feel? And the answer has to do with the amount of electrons that are shielding that nuclear charge from the outermost electron. So electrons in between the nucleus and the electron of interest, or the outermost electron, will cancel some of that nuclear charge. However, one key thing to note is that electrons either in the same energy level or outer energy levels do not shield effectively. And so what that means is, as you go across the periodic table from left to right, the effective nuclear charge increases. And that is because as you're moving from left to right, you are adding an electron, but that electron is going in the same energy level as the outermost electron is going in the outermost energy level, which again, those electrons are not shielding each other. So you're adding a nuclear charge because each time you move from one column to the next, we add a full proton. We're also adding an electron, but again, that electron is going in the outermost energy level, and therefore it doesn't shield. So the idea is that effective nuclear charge increases from left to right. Now, as it turns out, my slide is wrong. This is telling us that effective nuclear charge increases as you go down. It actually decreases as you go down. And the reason for that is because let's take this element right here. It has one s electron, as do all of these elements. Okay, that's the outermost electron. But as you move down, there's another energy shell that outermost electron has to see through. And therefore, you're not going to get as strong of an attraction. And so effective nuclear charge increases from left to right across the table, and it increases from the bottom to the top. So again, this is incorrect. This arrow, I've been saying I need to change it for years, and I just haven't done it yet. But this trend right here, understanding the effective nuclear charge, is really what's going to allow you to describe all the other trends that we're going to talk about. And so the other trend that we're going to talk about in this little video has to do with atomic radius, which essentially is how big are the atoms. And again, it has to do with how strongly the electrons are held. The effective nuclear charge, as we talked about here, as that effective nuclear charge increases, remember, opposite charges attract each other. And so if that effective nuclear charge is stronger, then that nucleus is going to hold on to its electrons tighter. It's going to pull them in closer. And so the way that the trend works for atomic radius is, if effective nuclear charge increases, the atomic radius, or the size of the atom, decreases, because as effective nuclear charge goes up, that nucleus again has a stronger hold on the electrons and can pull it closer. And so effective nuclear charge increases from left to right, therefore atomic radius decreases from left to right. Effective nuclear charge increases from bottom to top, and so therefore the size decreases from bottom to top. So those two trends are intimately related to each other. Again, it has to do with the strength that nucleus can pull on the electrons, and the stronger it can pull, the smaller the atom is going to be. So this is just another way of representing trends in atomic radius. So lithium is at the far left of the periodic table. Fluorine is at the far right. So as you go across, as the effective nuclear charge increases, the radius decreases. These right here, the reason we see kind of this bottoming out has to do with the transition metals. But in general, again, the process is from left to right, the size decreases. And as you go down the table, the size increases because you can see lithium, sodium, potassium, and rubidium are all in the same family. Now, the question then becomes, well, when I have an atom, how does it compare to the ion? And you'll see that this slide right here shows how we can compare atomic radius with the size of the ions. And what you can always notice is that if electrons are lost, okay, so if we form positively charged ions, the atom always gets smaller. And again, that has to do with how strong the protons in the nucleus can hold on to the electrons. If you remove an electron from an atom, now that nucleus only has to it accounts for less electrons, and therefore it can pull them in closer. So as you remove electrons, the atoms get smaller. The opposite effect takes place when you add an electron. If you're adding an electron, that means the atom now has to account for one extra electron, and therefore things are going to spread out. And so, again, if you lose electrons, things get smaller. If you gain electrons, things get bigger. That can kind of be summarized by this reaction here, where a lithium atom reacts with a fluorine atom. And when they form ions, you can see the fluorine atom becomes a fluoride ion, and it becomes much larger. The lithium atom becomes a lithium ion and becomes much smaller. So in summary, we can say that a cation, or a positively charged ion, is always smaller than the atom from which it came, and an anion is always larger than the atom from which it is formed from. And so this is another kind of visual graphic to kind of show you that, and this is another thing that you can see as you go down the table, things get larger. Okay, and what you can also notice is these things that form multiple negative charges are larger than singly negative charges. And things that are multiply positive charged are smaller than singly positive charged. And so what we focused on in this video was, number one, effective nuclear charge. And that has everything to do with all of these trends. The stronger the nucleus can hold on to the electrons, the better it's going to be, or the smaller the atom is going to be, as well as the other trends that we're going to talk about here in the next video. So this is the end of part 1.